Have you ever spent hours troubleshooting application issues only to discover the application was never the problem? The server was running fine, network was healthy, firewall was configured correctly, ports were also open, but the application still couldn't connect. The real problem, DNS. I've seen many production incidents where entire teams spend hours restarting containers, checking Kubernetes pods, reviewing application logs, and even rolling back deployments. None of those actions fix the issue because the application never even knew where the server was. That's the power of DNS. Every single website you visit, every API call your application makes, every Kubernetes service lookup, every cloud resource you connect to starts with DNS. If DNS fails, everything that depends on it appears broken. And unless you understand how DNS actually works, you will spend your time troubleshooting the wrong layer. Today, I'm going to show you exactly what happens when your computer resolves a domain name, how DNS server work together behind the scenes, how caching and TTL work, how to troubleshoot DNS problems like a DevOps engineer. By the end of this video, DNS won't feel like magic anymore. It'll be something you can confidently troubleshoot in production. Before we jump in, if you are enjoying this networking for DevOps Engineer series and more hands on content with real production examples, make sure to like this video, subscribe to the channel, and share it with someone who is preparing for DevOps, cloud, SRE interviews. Now let's understand one of the most important services on the internet. Let's start with a very simple question. When I type google.com, how does my computer know where Google exactly is? It doesn't. Computers don't understand names. They communicate using IP addresses. So before my browser can connect to Google, it first has to discover Google's IP address. That's exactly what DNS does. DNS stands for Domain Name System. Think of it as Internet's phone book. Instead of remembering IP addresses, we remember simple names like google.com, github.com, aws.com. DNS translate those names into IP addresses so that computers can use. Without DNS, without DNS, you'd have to remember the IP addresses of every website on the internet. That obviously wouldn't be practical. Now let's understand what happens behind the scenes. When I type google.com, my browser doesn't immediately connect to Google. The first question it tries to ask, do I already know Google's IP address? The browser first checks its own DNS cache. If the IP address is already cached and hasn't expired, it uses it immediately. No DNS request is sent. If the browser doesn't have the answer, it asks the operating system to resolve the domain name. If the operating system already has the answer cached, it immediately returns the IP address. Otherwise, it needs to contact a DNS server. So, how does Linux know which DNS server to ask? Let's check that. I'm going to open my terminal here. In the terminal, I'm going to say cat /etc resolv.config file. Press enter. This particular file tells Linux which DNS server it should contact whenever it needs to resolve a domain name. You can clearly see we have a name server here. If this DNS server is unreachable or incorrectly configured, applications won't be able to translate domain names into IP addresses. As a result, websites, APIs, databases, Kubernetes services, and many other applications can appear to be broken, even though the network itself is working perfectly fine. That's one of the reasons DNS problems are so frustrating. Everything looks down when in reality the application simply doesn't know where to connect. Now let's see DNS in action and ask for Google's IP address. I'm going to run nslookup space google.com. Press enter. Notice that we are receiving so many different IP addresses here. At this point, we still haven't contacted Google. We've simply tried to ask what is the Google's IP address. Now let's use another tool called dig space google.com. Let's look at the output now. The first section here simply confirms our query. The most important part is the answer section here. If you look here very carefully, you will notice several different IP addresses. Google is not returning one single server here. This allows Google to distribute traffic across multiple different servers around the world. Now, let's look at this particular number. For example, if you see google.com 155 TTL and I can see in A and the IP address. So let's try to focus on this particular number. The number is 155 is called the TTL. TTL stands for time to live. This particular number tells DNS resolvers how long they are allowed to cache this answer. Instead of asking Google's DNS server every single time someone opens Google, the resolver caches the answer for a limited amount of time. That makes DNS much faster and reduce unnecessary traffic. Now let's prove that. I'm going to run this once again. Notice here the time is 5 seconds. This has decreased by almost 150 seconds. That tells us we are receiving a cached response. Once the TTL reaches 0, the DNS resolver will fetch a fresh answer from Google's authoritative DNS server. This explains why, after changing a DNS record in production, engineers often say, let's wait a few minutes. They are waiting for cached DNS records to expire. We do have other ways as well to clear that cached DNS. Now, let's try to query a domain which doesn't exist. For example, dig this domain does not exist 12345.com. Press enter. Now, look very carefully. The first thing I notice here is status NX domain. This stands for non existent domain. DNS successfully answered our request. The answer simply was this domain does not exist. If you look at the answer section, I do not see any answer here. There are no IP addresses because there is nothing to return. Notice something important here. This is not a firewall problem, also not a networking problem, application problem. DNS worked perfectly. The domain simply doesn't exist. That distinction is incredibly important. DNS worked perfectly. The domain simply doesn't exist. This particular distinction is very important during production troubleshooting. Now, let's try to understand a real production scenario. For example, imagine your application is trying to connect to api.company.com, but someone accidentally configured api.company.com. Here we can clearly see api.company.com, but here I can see ap1.company.com. Only one single character changed, the application never reaches the server. It never performs a TCP handshake. It never establishes a HTTP connection. It fails before any of that because DNS cannot resolve the host name. This is why experienced engineers always verify DNS before blaming the application. Whenever I suspect a DNS issue, I ask three simple questions. Number one, can the host name be resolved using nslookup space domain.com or dig space domain.com? Second, am I receiving the correct IP address? If you are deploying any application in production environments, you know the IP address of that machine, right? I am going to look for that. Am I receiving the same exact static IP address? Followed by the number three, which DNS server am I using? cat/etc/resolv.conf. These three simple checks solve n number of production incidents. Let's quickly recap what we have learned today. DNS translates domain to IP addresses. Your browser checks cache before asking DNS server. Linux uses the DNS server configured in /etc/resolv.config file. nslookup quickly resolves names. Dig provides detailed DNS information, including time to live. And also, time to live determines how long DNS responses stay cached. If DNS fails, if DNS fails, your application may never even know where the destination server was. Before checking ports, firewalls, restarting services, always verify DNS first. Because if DNS cannot resolve the host name, the rest of the network never even gets a chance. If this video helped you understand DNS better, comment networking below and let me know what networking topic you'd like to see next. In the next episode, we will dive into TCP, three-way, handshake, and watch exactly what happens before two computers exchange a single byte of data. Thank you for watching. I'll see you in the next video.